Hey, looks like we can start. Welcome back, everyone. So I've lost count of what week number we're on, but it's got to be week 12 or 11 or something like that. But welcome back. For today's class, I did forget my digital pen, so some of the drawings on there are going to look a little bit rough. But before I upload them to the Moodle website, our usual solutions, I'll clean them up with the digital pen when I get back home, so they won't stay rough. But we'll get through it and it won't be too bad. For the moment, here's where we're at to the progression of chapter 10. Our goal is to get to section 10.5 to put everything together and start testing hypotheses. Section 10.1, we finished last week pretty earlier on, with just setting up your hypothesis, null and alternative. That's quite a bit of a process just on its own. Then section 10.2 is where we spent most of the time last week getting through. That is a very tricky section. It's about type 1, type 2 errors, and those can occur on an exam. The final exam would be the one it would occur on. But the major takeaway was actually the significance level alpha. That's how we're going to decide if we even reject the null hypothesis and favor the alternative or fail to do so. So although type 1, type 2 errors are always going to be important, that was actually the bigger takeaway there. Then in section 10.3, we'll see how we finally use all of our work on probability theory to help decide if we're rejecting or deciding to fail to reject the null hypothesis. Then in section 10.4, that's the last missing ingredient we need for the full procedure before we put it all together. But the preview on what we mean by a test statistic is that's nothing but a z-score. We're back to chapter 3 on counting standard deviations, that something is away from its mean. So the course is really just kind of wrapping back on itself all over the place at this point in the semester. And we really feel it on exam 3. On exam 3, there's 3 sections on it, but really, we mentioned this in class. I'm not going to bring an official 8.2 question to a real exam, not exam 3 nor the final exam. It's on that list because 8.2 connected 6.5 with 9.3. So it's there because it was the material we got through. So our exam 3 will be a couple questions on section 6.5 dealing with the normal distributions. I expect a couple questions on 9.3, putting together interpreting a confidence interval. So that will be the entire extent of our exam. It's really kind of weird. On exam 1, exam 2, that was like a dozen sections practically. But now we're kind of focusing on the overall summaries, kind of like how 10.1 to 10.4 is going down to 10.5. And that's why you only see just a few down here. We'll still review for the exam 3 on Thursday, but we won't do as much reviewing for this exam since we still have to get through these before the end of the semester. So that's my spiel on the announcements. Any questions at all, folks, before we get started? Okay, also, I did want to put out just kind of a random reminder. We mentioned this at the very, very start of the semester about our quizzes, but it's been a really long time. The issues with quizzes are, it's just another way to do homework. We didn't call it homework because that's confusing with WebAssign being our real official homework. So always think of your quizzes as participation credit, really. They're graded really light, but the thing I want to mention today is, especially quiz 11 was a pretty hard one. You're absolutely welcome to ask questions for me on these quizzes, anything along the lines of, am I on the right track, or is this the correct value for maybe a parameter or something, or population characteristic, something like that. You're also welcome to work in groups, so that's always completely fine. And again, think of those as pretty much just participation credit. Where the graded 5 points of the 10 is really, you came to class, you showed up, handed in your quiz, so that's the participation. The other 5 points is just correctness. But any questions at all, folks, on that quiz number 11 or otherwise? Okay, well, so far we're now in section 10.3, and I like how our author called this. It's the logic of hypothesis testing. The official title is Logic of Hypothesis Testing, an informal example. So this is our author's chance to kind of tap on the brakes a little bit before the next section comes up. We've discussed a ton of information about hypotheses, setting them up and considering their errors. So now we're going to run through an entire hypothesis test. It's an informal example, so it's also essentially a preview of what the author's trying to indicate to us when we solve this problem. So what's coming back right away is the central limit theorem. And we probably expected this because that's how we did our first inferential procedure. We need the central limit theorem to just do confidence intervals. So now if we're testing hypotheses, the same exact theorem comes back into play. So it gives us a mean value. When you see the mean, think of the center. They'll give you a standard deviation. The standard deviation is given here. Think of how variable how the variability is for the data, variability, and it'll also give you some information about when the shape of the sampling distribution of p hat, our statistic, is approximately normal. It's the normality that we need primarily so we can get probabilities to be calculated. And we do need a calculated probability to get through our upcoming hypothesis test. So think of rule one as telling us information where the statistic should be next to. It's the center. Rule two is going to be the variability. And rule three, think about this one as the shape of the distribution. It's saying the shape is approximately normal. And I draw that on there, but again, I don't have a good pen to draw on these things. Yeah, go ahead.
Rule one is the center, rule two is the variability.
Exactly, variability, or I'd say another good word for that might be spread.
And then what did you say? Rule two?
For this one, think of shape altogether. So, yep, you betcha. Other questions at the moment? Okay, so with all that in play, this is actually enough information for us to do an entire hypothesis test. We only decided to do the confidence interval first because, and our author did as well, because it's much more direct to get into that process. So now with the central limit theorem here, we'll cite it as we go through the problem. Let's take a look at our example right here. It says, a court holds jurisdiction over 5 counties. The juries are required to be made up in a way, or excuse me, are required to be made up in a representative manner from eligible populations of these 5 counties. They tell us next, an investigator notices that the county where she lives in has 14% of the total population of the 5 counties eligible for duty. So that's the setup so far. This one's really about the legal system. And when it comes to the legal system and jurors, there's a very specific thing that has to happen, or else that legal system is starting to break down. And that specific thing is the juries are required to be made up in a representative manner from the eligible populations of those counties. So now there's an investigator into play, and that investigator says she lives in a county that expects 14% of the total population to be eligible for jury duty. So here's where the drama of the problem really gets going. They go and say, records reveal that over the past 5 years, 172 out of the 1,386 jurors used by the court reside in her county. So we're saying she's expecting 14% to be eligible for jury duty, but only 172 out of a sample of 1,086 were actually selected to be on the jury for jury duty. Then they go and ask us a question. Do these data provide significant statistical evidence that fewer than 14% of jurors are being selected from the county where she lives? So that's our whole statement of the problem. And again, for these kinds of questions, good to read them a second time, a third time even, maybe even a fourth time after you've solved it, just to make sure our idea of the problem really makes sense once we've completed it. We saw a lot of numbers, so let's go through these and see if we can indicate what they might be. 14% came up twice. It came up in this second sentence. Let's highlight this in gray. One big trick in a hypothesis testing is if you notice a question is being asked of you in the statement of the problem itself, that's probably the alternative hypothesis. 14% appears again in that question. So let's start by writing out this. Pretend for the moment that this is a digital pen. I'm going to revise this and really write it in as a pen. But the first value we have is P naught. It came in as a value of 14%, indicated right here. So let's turn it into 0.14. It also came up here, so it's being used twice. Next value we have is, well, there's 172 out of the 1,386 jurors used by her court that reside in her county. It looks like this might be considered to be a sample size. We just don't have any information of that being random. In fact, we know it's not random. That's just purely historical data. So this is not the greatest problem. We don't even have random data. But keep in mind, it's an informal example, so we'll just do our best with what we can with this problem. So let's consider the 1,386 a sample size. We'll call it n then. Then we're dealing with categorical data, so we should have a notion of what a success would be. That could also come from the practical question they're asking. They're asking, is there evidence that fewer jurors than 14% are being selected from the county where she lives? It sounds like a success is being selected from the investigators county. We can say that there is 172 successes. So it looks like that's all I could really find in this problem so far. Does that look right to folks with the information that we pulled out? Okay, just for the sake of color coding, let's go with green on that one, and let's put, or excuse me, blue on this one. I know my colors, I swear. Blue on this one and this one as well. Yeah, go ahead. Good call on that one. That's one I totally neglected, but that's kind of like the most important thing to take a look at. When we go through the problem, we have no idea if we're rejecting the null or failing to reject it if we don't indicate that. So thanks for mentioning that portion right there. Let's write out alpha. Only because they said level of significance, we're going to call it alpha equals the 0.05. And that one deserves a very, very special color. Let's go with, this is definitely the new thing, so let's use purple on this thing. So this is the reason we're really doing what our author calls an informal example on our way to section 10.5. We just need to be familiar with what in the world to do with that thing. But any questions at the moment? Okay, let's add just a really quick comment right here. A probability smaller than 0.05, let's call that alpha since that's what it is, will lead to a rejection of H naught. And a large probability, let's say here, a probability larger than alpha equals 0.05 will, let me fix that word there, that's a L for leads to, will lead to us failing to reject the null hypothesis, which I'll type in as H naught. So now we have a feeling of what counts as really good evidence. Once they set their significant level at 5%, they're balancing type 1 and type 2 error. But now a probability that we'll calculate will be considered small if it's smaller than that 0.05, and that's what's going to cause us to reject a null hypothesis in favor of the alternative. We still haven't written down the hypotheses, but we're about to. And now we know what we're going to do with that alpha value, which came from, let's highlight it also right here. It's really a vocabulary kind of question because the problems are most likely going to say significance level or level of significance. We just have to know they're referring to alpha when you see that word verbiage coming up in the problem. So now in part A, we're going to define the population characteristic or parameter using the context, state the null and alternative. Any questions at all first? Okay, let's start with the population characteristic. Our data is all categorical, so we're going to be using P to stand for proportion. And we can write out something along these lines. P equals the true proportion of, let's go to the highlighted portion here to get a feel for successes, or what we wrote down here. A success is being selected from an investigator's counting. So it'll be the true proportion of all jurors who were used by the court and live in the investigators county. The way I wrote down this population characteristic P here is in a slight conflict on what I said for the successes. Let's take another look at that. I said a success is being selected from the investigators county, but what I want to emphasize is not just being selected, but actually used by the court. I don't know if that's a huge conflict. How do folks feel about that? Is that okay with what we wrote down on P versus what we said here on the success? Okay, so I think we're okay with that. So we're going to consider the successes a success of actually being used and present for jury duty in the court, and that's the proportion P. The investigator says, after looking at historical records, it should have been 14%. And we can use that immediately to write down both a null and alternative. Let's go and write H naught for null. It'll be the statement that P, the same P that we just defined right here, equals 0.14. So that came directly from the value to be tested, the hypothetical value right here in the question. Next portion is the alternative hypothesis. The null, just as a reminder, is always great. If you found the value that's going to be tested, you're always going to put directly equality right here. The alternative hypothesis has to be fine-tuned to what they're really wanting to investigate. So the question said once more, do these data provide significant statistical evidence that fewer jurors than 14% are being selected? So because they said the word fewer, would that be P is the less than symbol or the greater than symbol or a not equals? Exactly, with fewer, we'll go with less than right here. Again, that's always kind of problematic in a way. There is exactly one word, there it is, that decided the direction right here. Let me go put in the value. It's 0.14. I'm going to put something here that's extra and definitely optional. So if you didn't write this in, that's okay. But this is the really good place to insert the significance level alpha, because it tells us what we're testing and the level of evidence we're required to have when we make that test. So I'll put alpha right here equals 0.05, just as a reminder. So we did it, folks. We have our value for P indicated right here. I'll use blue again since it goes here and here. The 0.14 we also selected from above goes in that location. And significance level, always a good thing to keep our eye on that number right there. When we go through the process, we parked it right below. So that's how part A goes. Whether we're doing a confidence interval or a hypothesis test, we'll always indicate P. And this is just the extra information if you're doing a hypothesis test. Let me highlight that in yellow to show where it came from. And blue there. Well, let's go off to the follow-up questions. Here's the way we're going to begin to use the central limit theorem above. Let's take a quick screenshot of this. Part B is asking us to describe the shape, the center, and the variability of the distribution of p hat. The reason we're doing that is we're going to have to calculate p hat, and we'll need to find the probability of finding data as extreme as 172 successes when the null hypothesis is actually true. So before we could do all that, we have to cite the central limit theorem and figure out all three of these values, the shape, center, and variability. So once again, let's figure out the color coding here. I pre-highlight that in yellow, darn it. Well, let's keep that in yellow. That's a pretty important statement there. But for shape, what we're doing is checking this rule right here. So here I'll just write for shape. We're deciding if our data, the actual real data we have, is going to be normal enough so that we can have it, the sampling distribution of p hat, approximated by the normal distribution itself. And it's the same kind of checks that we do, n times p times n times 1 minus p, but it's a little bit different. When the formula is written this way, and when we're testing hypotheses, here's what we actually have to calculate when we check the conditions. Let's make a big warning right here. Or caution, let's go with warning. It sounds more official. For confidence intervals, we use the data from the problem, let's say the data collected from the problem itself. Now, when we test hypotheses, we're going to do this a little bit differently. This is the reason this is highlighted in yellow. The moment you've assumed the null hypothesis is true, and that's the very first step in a hypothesis test, you've assumed a value for P. It is now going to be assumed here and forevermore, it's 0.14. That deserves a reset on the highlighting. It'd say, we're assuming this is true. So for the purpose of the test, we're going to put 0.14 right here, and everywhere else P occurs in the formulas. So that's a huge, huge statement what we just made in a hypothesis testing, assuming our null hypothesis is true. So back down from the warning, we can now say, in hypothesis testing, we use the value from H naught, not H naught, H naught, and write P is 0.14 for determining normality, or if the curve or the sampling distribution is normal enough. So that's how we're going to assess the shape parameter or the shape population characteristic on this thing. Let's now just take n times p, n times 1 minus p, and calculate those values. So let's say here, n times p is going to turn into, let me scroll for just a moment. The sample size n is the 1386 we see here. It's multiplying at 0.14. That's a pretty fast computation. 1386 times a 0.14 gives us 194.04 successes. Now, if we had actual real data, and this was a confidence interval, that 0.04 would have been impossible. You would have had an exact success, or maybe something that rounds very, very nearly to that value. Well, for our current problem, this could have been very far away from 194. It could have been 194.33. It's still the correct value, even though you can't have a fractional amount of a sample size. The reason this is okay is we're really thinking of this as the expected number of successes we would get when we do this study over and over again, assuming the null hypothesis is actually true. The average value of successes should settle around 194.04 after repeating the study. So it's okay to have a decimal number right in that location. The next thing you can do is take this formula, n times 1 minus p, and show it's greater or equal to 10. Or you could just take the 1386, subtract the 194.04 just calculated, and it'll give you the same exact figure. So let me put down on paper, we have 194.04, which is definitely greater than or equal to 10. And next, it is n times 1 minus p. But here, let's just use the shortcut, cite the value, 1191.96. This is also greater than or equal to 10. Forgot my 10 right here. And because both of these are exceeding 10, that's our benchmark that was indicated down here. We can finally say, for this first part of this problem, where it says shape, we will say, since these counts are both greater than or equal to 10, the shape of the sampling distribution of p hat is approximately normal. And that's the thing that we want to check. Now that we have normality in the problem, we can use our ordinary calculator right here, use the normal distribution, and get a p-value out. We'll compare the p-value against the alpha 0.05, the level of significance. But any questions or comments at the moment, folks, so far? Okay, I do notice one thing that is really bad for forgetting a digital pen, especially randomly like I did today. I type a lot faster than I write. So if I'm going too fast and you're writing down stuff, please let me know and I'll pause on that screen so we can all get caught up. It just feels like I'm a little bit not quite at the same pace as normal. Well, we did the shape. Next thing we'll take a look at is center. Any questions or comments or any additional time folks need at the moment? Okay, well, for center, we're really just going back to this right here. Rule number 1 tells us what the center should be for these kinds of distributions. And it's a wonderful computation. But when you do this kind of question, when you do it in, say, WebAssign as well, it's all about that statement highlighted in yellow. That's why I decided to keep the yellow highlighted right there. The center is not something we've ever been able to calculate. Until today, we can calculate it because we have the value for P right away. We're just going to put in a 0.14 and say, center is mu P hat. We're saying the center of the statistic P hat, the typical value we're expecting. We're expecting a 0.14 if the null hypothesis up there is really true. That's what that value should be most closest to. There is variability, and so we have to take a look at what the variability says in the problem coming up next. But here we have our center. That's the value we've been looking at for quite a while. And next, let's go to variability. We're just doing one of those again, but it's different. We're not using p hat because we don't have to make that estimate. The only reason we used p hat earlier is because there was no null hypothesis when we were doing those confidence intervals. So we had to use the standard error in the typical way by just throwing a p hat formula or p hat value in 2 locations. This time, we're going to plug in p, the assumed value of the population's proportion from right here. So next, let's call this variability. It's going to be sigma. We're talking about a population standard deviation. We put p hat just to say we want the deviation of the statistic p hat itself. So this will tell us just how spread out the values are going to be around the center of 0.14. If that spread is huge, then we might not have very great accuracy or power in our test. But if that variability is tiny, we expect high accuracy when we say we rejected the null hypothesis or when we say we failed to reject the null hypothesis. So variability is going to be, we called this standard error p hat in the earlier notes. So if that helps to remind you, that's not a terrible thing to put in there, right in that location. And it's this thing once again. It'll be square root of, formula indicates that p times 1 minus p divided by n. It's definitely down below there, but that's a temporary screenshot, so it's good to have it available in the notes. We can fill out some of these pretty quickly. The sample size n is the 1386. Better to look at the original value in case I typed that in wrong. Yes, 1386. Then up above, where it says P, we're going to throw in the value directly out of the null hypothesis. And when we do this as confidence intervals, again, this is very, very different with a confidence interval. The point of a confidence interval is to estimate P. We never assume a value for it once at all when we do that whole process. But now down here, we're going to throw in a 0.14 times 1 minus a 0.14 and calculate that value right there directly. So this one is not an estimate. This is the true variability or the true standard deviation of that statistic p hat, assuming, once again, the null hypothesis is really true. If it's patently false, we're going to find out very, very soon, because the more false this is, the more incompatible it becomes with our data, and our p-value is going to become larger and larger because of it. But finally, let's go and get a value out to the calculator for this thing. We've done a lot of these, but it's always kind of a tricky thing to put in. Let's go second key, square root symbol to start. Then I'll do the strategy of just going inside the function, write everything out. 0.14 times 1 minus a 0.14. Close that parenthesis, then divide by 1386. And here's our first standard error for today. It came out as a 0.0093, 2 if we kept some extra accuracy. Any questions at all, folks, on getting that number? Okay, let's throw that in, 0.0093. They might have said something about rounding. Let's take a look here. Nothing about rounding. That might have been an omission on my part. Let's keep 4 places then. That should be about what we would have done in WebAssign. So 0.0093. So finally, we have our variability. We usually use green for that, so I'll keep this as a green figure right here. So that's finally the end of our part B portion right here. We described the shape. It's normal. We have a large enough sample size for that to work out for us. The center is at the direct value of the null hypothesis. And the variability, it's not too bad. That is pretty small, probably largely in part with our sample size right here. Well, with that all out of the way, we're done with the central limit theorem down below here, and I'm not sure how to delete it. Oh, there we go. And so now what we're trying to calculate are the so-called p-values. We're going to define that and make that precise when we go further in the notes. But we're going to start calculating probabilities. We're going to keep our eye on that alpha as well as the alternative hypothesis. We might as well bring this down as we solve the rest of the problem. I put these shapes here because I knew I forgot my digital pen, so this is just my really fast way to try to get a shape. These kinds of problems, you don't necessarily have to put that curve there if you feel confident in your section 6.5 on normal distributions, but it's definitely good for the notes. That's why you're going to see them on these problems here. So part C says, would you be surprised to observe a sample proportion as small as p hat is 0.13 if the null hypothesis were true? Explain why or why not. I wrote out these instructions pretty much verbatim the way we're going to see them in WebAssign. It's kind of a strange question, but here's what we're trying to answer with this type of question. Assuming H naught is true, we want to determine the probability of obtaining data as extreme. Let's put some italics on that. As extreme as p hat equals 0.13 or more extreme. That's what a p-value is really trying to assess. What is the probability of getting a 0.13 if the true proportion was 0.14? Well, I can't actually give that probability. That's probability 0. But I can answer it if I say or more extreme. The reason for that is the normal model has one weird defect. I think we did talk about this at least once. I think this was a question from class. The normal distribution has this interesting, some might say a defect, some might call this a feature, but the probability of a value taking on anything is 0. If I put a less than right here, I would get a non-zero probability. And that's what the or more extreme is all about. We're not trying to calculate the probability of p hat is 0.13. We want the probability it's 0.13 or more or less. It's going to depend on the problem. But more extreme than that value is what we're trying to calculate. Now we have a normal curve, but we have these values. P hat is 0.14. Standard deviation of p hat is 0.0093. Not going to be able to draw them on there too nicely, but that's okay. We might need those quite a bit as we go through the problem, so we'll take it along with this one. Let me just make these a little bit more manageable size. And here's what we're going to calculate right away. We want to calculate the probability that our statistic, which is going to be p hat, this is where the x would have gone on those prior problems when we were section 6.5. The x value would have gone right here. We're going to take the 0.13, and now we have to put something in the middle right here. Same kind of question, actually. We need to decide if it's going to be a less than, a greater than, or a not equals. So one of those 3 options has to go right inside there. Has anyone spotted which one would be the correct option? It turns out it's not greater than in this case. There's definitely a hint though. What you want to take a look at is your alternative hypothesis. We'll always tell you what's really going right exactly here. And in our alternative hypothesis, we're testing a less than. We want to know if 14% or fewer was being selected from that particular county. And because of only that right there from the alternative hypothesis, we'll go and put a less than right in that location. Let me put just a quick note.
Taking this from our alternative.
Exactly. Let's put that as our official note on this one. Trying to just get the graphics. There we go. So we'll say here, we use less than in the probability function only because of HA, P is less than 0.14. Let's say only because of the less than sign in the alternate hypothesis. So that's the only reason we select that sign right there. And let's connect those thoughts. We use the less than here and here, all because of that alternative hypothesis. I can't put it here because when I type it moves, but I'll try to get that highlighting on the very end. But again, I'm going to revise these notes a lot in the morning tomorrow because of all the weirdness we see here, make it more familiar to what we're used to seeing. So now we have the right direction. The next thing we should do is, let's also give this a name. The typical name for what we're calculating right here is, it's the p-value. So we're calculating a p-value, which means we're automatically comparing this against a 0.05. But we have to put this on the graph here as well, since I can't calculate this whatsoever unless I know what the picture looks like. So in our picture, we have a center at 0.14. Let's see if I can draw this reliably. So right here is 0.14. That's pretty terrible, but that'll work. We're testing a 0.13, and the standard deviation is about a 0.001 if we round it to that position. So 0.13 would be right around here. This creates a barrier that goes into this location, and now we want to shade all of the area towards the, oh, that's terrible, all the area towards the left in this way. I'll just kind of highlight it generically like this. Now, I don't have the typical things I would have said, but I would have said the lower is -10 power 99, 0.13 is upper, and here's your value of mu and your value of sigma. So the calculator, here's how it all gets imported. P-values is always a normal CDF process because we're always trying to find an area. So it hits right away, second in bars, go down to option 2 for normal CDF. We want this blue area that was drawn kind of haphazardly. So to get that, start with -1 e power 99, or this is what you'd probably normally see. -10 power 99 does the same exact thing. Our calculator has a weird way to do scientific notation. Our upper value is right at 0.13. And then finally, values for mu is 0.14 that we calculated, the center from earlier. And our variability is the 0.0093. So all that should give us our area in this location. It comes out as a 0.1411. And I'd say 4 decimal places is very, very typical for a p-value like this. So let's take a 0.1411. And we did it, folks. Yes, go ahead.
So the first one was -10 to 99. The second one was 0.13.
Yes.
One was 0.14, and what was that second one?
It should have been, yes, 0.0093. I was just double checking if I got it in there right myself. Exactly. So that value right here. Yep, you betcha. Other questions so far, folks? Okay, now that we have this p-value right here, there's a couple things we could do with it. Let's put down an interpretation. This is not required, but it's sometimes informative to know what that is even saying. What probability did we actually calculate? So here is not a practical interpretation, not by any means. This is a probabilistic one. Let's say it this way. Probabilistic interpretation. There is a 14.11% chance of obtaining a statistic as extreme as 0.13 or more extreme. We know more extreme in our data, matching the alternative hypothesis would just mean smaller, but that's a good generic statement to make because direction depends on the problem. Extreme depends on the problem, essentially, or more extreme. And here's the big statement, assuming that the null hypothesis H naught P equals 0.14 is really true. So if that's really true, well, we have a pretty large chance of that happening. That would happen out of 14 out of 100 studies. And that means it's not necessarily a rare event at all. Our data is compatible with the null hypothesis. If it came out like this, however, we would have said our data is incompatible with the null hypothesis because that would only happen 1 out of every 10,000 studies. But this is way typical. That's not the full story because what do we do if the probabilities are borderline? They're kind of small, but kind of big. You could have an entire argument, a huge debate, possibly a brawl over this kind of stuff. And that's what the alpha level right here is all about. It's giving us an actual figure so that we'll make that decision no matter what happens to the data once we calculate the p-value. So we decide on this even before the data is collected. Even before you have any notion of what the data looks like, all these values are put down on paper and you have to stick to them through the entire test. There's no takebacks, in other words. And if you did, you could lose funding on that problem. You could be accused of being unethical in statistics. So we'll go over here. The moment you see this, immediately compare it against something else. I'll write that this is greater than 0.05, which is equal to alpha. And all that deserves purple. We can say now down below, to finally address the original question, they asked us, should we be surprised if p-hat came out as 0.13? And we can now say, no, that's not surprising. This is not surprising since the p-value is larger than the significance level alpha. So we would say this is, oh geez, I don't know what I hit on my computer here. That's got to be accessibility. So larger values are not surprising. And we can also say here, we will fail to reject H naught. That would be essentially our conclusion in this problem. So for a value statistic like that, that's what the scenario would be in this problem. And the way this question is going is they turn it around on us, same as in WebAssign, and say, okay, so a value of 0.13, not surprising, but what about 0.12? We're just doing weird scenarios. Then finally, part E, we'll return to the original sample data and test our actual data. So think of parts C and D that we're looking at, kind of a preview of what is happening really when you go to test these hypotheses, compare the p-value and such against the significance level alpha here in purple. Well, let's see if we can try it one more time and see what happens down here in part D. Any questions so far, folks? Okay, so for this next one, We're going to analyze it in the same kind of way. Let's take this. I think it goes a little bit better over here with the way we're putting graphics on. We're testing a value at 0.12, so let's draw first the center, still right here at 0.14. But right where the red dot is, that's about 0.13. Right around here, I would say that looks like a 0.12. Now, 0.12 is pretty far away. If the null hypothesis is true, we're expecting our statistic to land right around here, near the center. So if it's far away, that is a surprising result, and that becomes incompatible with the null hypothesis. But we need a probability, and we need to show that probability is a less than a 0.05. On paper, here's how it would really go. Once I get this to work out, we'll calculate the probability that a statistic, p hat, is less than, now this value, 0.12. Oh, and it's a good idea to call this a p-value like we did before. So it's a pretty fast computation because it's pretty much in the calculator already, right? You can open up your calculator, and I already have it on the right page. Hit second, oh, let me clear out of here. Hit second bars to go back to that page. We're back to normal CDF. And I needed the -1 e power 99, or the way we did it for this problem works. Upper value changes to a 0.12. And they delete my values here. Let's look at those up again. The value for mu is 0.14. Value for sigma is 0.0093. Now, finally, in this picture, we're finding the area right here by the red dot, and it comes out as 0. Was not expecting that. Someone else probably have a better value than 0. Let me see what I did wrong here. Second bars, normal CDF. I mean, I know it's small, right? It should be pretty small. I definitely have something in there wrong. Oh, I see it. I said mu is 14 without a decimal value. That would take us extremely far away from that center. So let's put in a 0.14. Okay, now on our second try on this, I get a p-value of, that's about more what I was expecting, a 0.0157 or 58 after rounding. So 0.0158. We immediately compare this against the significance level alpha, but this time it's less than 0.05. So because of this directionality right here, we found a less than a 0.05, which is alpha. We can say, yes, these data is very surprising since the p-value is smaller than the significance level alpha. This is a good reminder for me to not forget my digital pen next time. I appreciate everyone's patience. This is not easy to do, but I think we've got it, folks. Just want to connect the color coding here to here. Here to here. I guess the last thing we can say, just for the sake of parallelism in this problem, is here we will reject H naught. We really will reject it in favor of HA. We'll be practicing on writing out those practical interpretations, but we already have a pretty good background for doing that. It wouldn't be too bad. Well, when we come back on Tuesday's class, on part E, we're going to test our data and see what happens with our data, and we'll write out that practical conclusion. But any questions or comments at the moment, folks, with the way the notes ended? Yeah.
Okay, so it's smaller than the significance level, and it's surprising if it's higher than it's not surprising.
Exactly, yes. And one thing you might have noticed is there's no value right at 0.05. But that is such an extremely rare event that you get exactly 0.05 as your p-value that a lot of books don't even worry about it. But what you could do is put greater than or equals on this one if you're worried about that extremely rare event on that location. We want things that are strictly smaller down here in order to reject the null hypothesis. So less than should always go on to that one. Well, any last questions, folks, before we call it a night? Okay, well, have a great evening, everyone. Try to stay dry out there. And this is where we'll be when we come back on Tuesday. And I'm definitely going to revise these notes, make them a little bit more readable when we come back. So they won't look this weird when you look at them again on Moodle.